Hi guys, can I get a sound check?
Sounds good.
Great, thanks guys. Let's see. What was I doing? Just 1 second, guys. I'll get my act together here. Let's see. All right. Okay, sorry about that, guys, but I think we're ready to go. So let's see, where were we? So following up from, when was the midterm? Was it Tuesday? It was Tuesday, right? So we had like lecture on Thursday. We did. Boy, my memory is shot to head. Okay, so I just wanted to like take a step back, and I think I mentioned this during our lecture, but I thought I'd mention it again because it's like generally like very important, and I didn't quite get this while I was in undergrad. I don't think I really got it in grad school either. But so we mentioned this a couple of times, but the important parameters that make, gives the sort of the quality, let's call it the quality of a design. When you're in undergrad or grad and you're doing projects, again, even in the PhD program, etc., we're almost entirely focused on one quality of the design, but there's a bunch more, and that's the quality of, say, performance. Like, in this class, it's like if you have, it translates to, let's say, the speed of your circuit. Like, does your chip run at, for example, does your chip or circuit run at, and does it run at gigahertz, and does it run at 2 gigahertz? You're a hero if it runs at 6 gigahertz. So like, how fast is your circuit running? If you're like, doing some other class, let's say, we're building an engine, it'd be like, I'm just, again, trying to make this, I believe this is pretty universal. If you were making designing a car engine, it'd be like, well, how many horsepower was your engine output? Now, that's just like the raw performance coming out. And so we're almost always focused on those. But then we said, look, there's actually some other parameters that determine how good a design is. Okay, so the second one is how how tolerant is the design tolerance, like how unbreakable is the design. I don't know how you want to call it. So tolerance, how unbreakable is the design. design. So for example, in our class, we talked about noise margins in our circuits. We'll talk about a bunch of other things about that. Like, if we use the analogy of the car engine, it's like, well, if you put in anything other than like, 91 like super unleaded gas in there, does the engine blow up? Or does it work just less well with, sort of less good of a gas? So you have to so this is the first thing that you realize when you go to industry, is that not only does your speed of your circuit have to work, they have to operate a certain way, but you're selling that to a customer that might be, use it, might use it really. I mean, think about how you guys use your cell phones, your electronics, your cars, your bicycles, whatever. There's just a bunch of variations that happens, stresses that happen in real life, and you expect your thing, whatever it is, you expect your cell phone to work even if the weather outside is 40 degrees, not only when it's like 72 degrees, right? You're just expecting your PC to work, even if the I don't know what that's a good example is, but even if your room is like it's hot, say. Those are sort of some examples, right? So those are tolerance. So again, in our circuit, talking about noise margins. These are always important. The third one is cost. So this would be development cost. So upfront engineering development cost and cost per part. Okay, again, completely ignored in school, right? Almost, at least where I went to school. You never think about, well, okay, that design was really gangbusters, but it cost twice as much to develop the product and took twice as long, so it got to market too late. So too bad, nobody wants it anymore. Or great, the car that you designed is really awesome, but it costs $500,000, and only a few people are going to be able to afford it, so they're kind of screwed. So cost is always important. In our case, it goes to how big your chip is, your chip circuit, because that's a cost per part. And then the second thing is how type of a process you have to use. So like if you had to use a 65 nanometer process, it would be more expensive than 130 nanometer process. Again, cost is extremely, like it's a figure of merit, just as important as anything else. If you get a good high performance thing, but it's the wrong cost, it's not going to work. Okay, so that's the other one your designer is going to be judged by. And the fourth thing is what we're talking about in this lecture, which is power consumption. And again, I can't think of a single, again, not at all addressed. I never worried about it in grad school or undergrad. Like, you're just happy your circuit works. Doesn't matter how much power consumption it took, at least in my experience. But in almost every case, it's hugely important. No matter what you're doing, the power consumption of the circuit is extremely important. Or how much gas if you've got your engine's running at like 5 miles to the gallon, again, like not a great product, right? Nobody's going to be happy about that. So that's the topic of today's conversation. But in one way or another, everything we talk about in this class is kind of like circling around these four issues, I think, generally. Okay. And they're all sort of trade, they, I don't say always, but a lot of times they end up being sort of trade-offs against each other. So, and like one of the really big trade-offs of power consumption versus performance. Typically, the faster you run, the more power consumption your circuits take. So in CMOS, as I think we'll see in a little bit, actually we talked about this earlier in the speed part of the lectures, was that we are charging and discharging capacitors, and how fast you charge and discharge those capacitors has to do with how much current your circuits are using, are able to pump out and sink back then. Okay, how well your PMOS transistors, how much current they have to push into a capacitor, and how much current your N MOSFETs have to discharge that capacitor. And as we'll see, the more current you use to go faster, the more power consumption you'll take. Okay. Second thing is we saw, in terms of tolerance of our circuits, like the higher our supply voltages are, the more noise margin we have. Okay. But as we'll see, the more the supply voltage, the more power consumption goes up. So we'll see some of these trade-offs. But anyway, that's what we're talking about. But I wanted to just remind you guys of these guys. And that, it's always, almost always, if you are on the lookout for, no matter, if you kind of go a couple of layers above the thing you're doing in that particular point, you'll see that for all these things will be true. So, I use the car example. Sorry to be long-winded here, but I think it's just that you don't see these three things until you get out of school, but they're very important things. For example, a bunch of you guys are computer engineers. I'm sure you're doing, coding, software classes, but, when you're doing software, running software, you're probably just focused on whether it's how fast, your software is running, say, or just does it meet the functionality. But if you don't do, what you'll see in industry is development time for the software to actually write the code is actually much shorter than the amount of people, hours, and schedule that it takes to validate the code, just to make sure that code works. So, and try to see if you can break it depending on the user. That's a huge part of the activity, and it usually, it really informs what you do with how you write the software, how many lines of code, how many sort of test points you have, watchdog circuits, etc. And same with the development cost of the code, how long it took you to write the code, etc. It doesn't so much software it's unique as that it's generally considered free, so there's no cost per part. It's really mostly the development cost of the software. And power consumption is kind of a little bit peripheral, but I guess you could kind of look at it as if the code isn't, and I'm trying to really stretch this analogy, but maybe if it's the code isn't efficient enough to run on a particular processor, so you have to go to a bigger processor to run the code, or if it if you need a whole lot of stuff to run it, a big system, then it tends to be into a problem. I think a good example we were talking about today with some friends was Bitcoin mining, right? So it's turning into I guess by nature that's meant to be using a lot of processing power, but just the power consumption and the amount of the cost of electricity ends up being important. So I think even in software, in one way or another, these four things will show up. Okay, so anyway, so we're focusing on power consumption. That's why we're focusing on it, because it's almost always important. And, we were sort of laying out these definitions of instantaneous power, the energy, which gives you this average power. So we really want to know the average power, because the instantaneous power could be anything, but really when you mostly talk about power consumption, you're mostly talking about the average power consumption. But we have to keep track of this as well, just to be able to calculate this. Okay, so we defined those. We looked at, how the power through the supply was the instantaneous current times the supply voltage. The power through the resistor is V squared over R. And the energy, you can't really talk about the power into a capacitor, but you can talk about the energy it took to charge the capacitor to a particular value. And that's ends up being half CV squared. Okay, so we have these parameters. And now we're going to try to apply it to our CMOS driver. Okay, to see how much power consumption this guy takes given a certain capacitor that it's trying to drive. Okay, so from what is this thing doing? So let's see. Let's say you're trying to take this capacitor from 0 to 1. So what you're trying to do, let's say this capacitor was at 0 volts, and then you're trying to get it up to VDD. So that PMOS is on, charging up this capacitor. The NMOS is off, so it's out of the equation. So basically, you've got this guy, this PMOS. It's outputting a current to charge up this capacitor. Okay, so regardless of how long that takes for a second, the total energy to charge up the capacitor is, as we saw here, is 1/2 CV squared. Okay, so we're trying to charge this capacitor to a voltage of VDD, which is a 1 for us, a logic value of 1. So the total energy to charge up this capacitor is 1/2 the value of the capacitor C sub L times VDD squared. Okay. Now, the interesting thing though is if we figure out as this event is happening, as this guy is getting charged up, if we actually look at what was the power we took from VDD, we'll notice it's actually bigger than this. So if we calculate the power based on this current times VDD times this amount of current that was required to charge this capacitor, we actually end up with twice that energy. So it turns out that we pulled CL VDD squared from the supply, but only used half of it to charge up the capacitor. Okay, so there is a missing 1/2 CL VDD squared. And the question is, where did it go? So again, this is the power. We have a certain power we pulled out of the supply. Okay, and a certain part of that was to charge this up. Part of it disappeared. And that part is really the energy that was dissipated in the PMOS transistor. The PMOS transistor has basically a certain resistance. And when you have current going through a resistance, that turns into thermal power. So basically it's sort of heating up your PMOS transistor. Okay, and then next, when it's the turn to now go from, so this was a transition from a 0 to a 1 value. Now you want to transition from a 1 to a 0 value. So in that case, you turn this guy off. This guy is at VDD, and you want to discharge it to ground with the NMOS. Okay, then you just discharge it to ground. Okay. Now notice in that case, we are disconnected from the power supply. Right. So we're only pulling power from the power supply when we're doing a 0 to 1 transition. When we're doing a 1 to a 0 transition, we're not pulling any power out of the supply. We're just discharging this load capacitance. And it, by the way, that is also, so that energy that was stored in the capacitor, when it gets discharged to ground, so this is the energy that was stored in the capacitor, it turns into heat in this NMOS. I shouldn't put a cross here, it just turns into heat. So it's sort of radiating heat. Okay. So that's sort of the sequence of events of charging and discharging the capacitor. So let's now look at what kind of happens from like sort of in a more detailed way. So this is an example of the same circuit. So we've got our inverter or CMOS inverter. It's connected to a supply. The example is for I guess a 65 nanometer process. So the supply is a 1 volt supply. The load in this example is 150 femtofarads. And the circuit is operating at a gigahertz. That means, so gigahertz means the period of input waveform is a nanosecond. So that period is 1 over frequency. So if you look at here, so this guy's transitioning from this is the input here. So this is time. And the overall going from high to low to high takes a nanosecond. This 1 is a nanosecond. Okay, so that's the input. So it stays high, goes low, stays low for a while, goes high again, comes out. And then if you plot the output voltage, you'll see that, when the input goes from high to low, the output is going from low to high. There is a delay. There's a propagation delay from here to here. That's our prop delay. And there's a prop delay from here to here. Okay. And then there's a rise time on the output and a fall time. All of it, which we know sort of how to calculate or at least estimate from the previous lectures. Okay. So that's what the waveform looks like. Okay. Now, if we look at the various currents, if you look at the current through the PMOSFET, okay, the PMOSFET is off here. They input it when it's a 1, right? When this guy's a 1, or when this guy's VDD, this PMOS is off. So there's no current flowing. And again, so as long as this is a 1, there's like no current flowing. Okay. As soon as this guy goes low, the PMOSFET turns on and current starts flowing to the capacitor. Okay. And so what happens is, remember that just if I draw like a transistor current, so VDS, there's IDS. When the PMOS turns on, it's in saturation. So it looks like a current source in this over here. So basically the equation for it here, it's in saturation. So let's say I sub P is VGS minus VT squared times beta-ish. So it's like a current source. So it looks like we've got a current source that's charging a capacitor. So this is while we're in saturation. So as the output goes from 0 to someplace out here, as long as this guy is in saturation, okay, as long as so it's from the 0 voltage to somewhere out here, it's in saturation and looks like a current source. So it's like, it looks like a very, and if you look at Q is equal to CV, dQ dt is C dV dt, and this is current over C is change in voltage with respect to time. So if you look at a current source driving a capacitor, so this is the current, this is the capacitor. It just looks like it's a constant value. The change in voltage with respect to time, which is the slope of this. So it would be the slope of this. Looks like a straight line, kind of, right? So here we just have constant current flowing. Okay, it goes up, 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 and then it gets to a certain value, right? It just stays constant for a while up here. Okay, and then at some point you get to the point where your device goes into linear operation. So now it looks more in linear mode. It looks more like a resistor pulling up this Isabel. And here the current equation is I sub D, or I should say I sub P beta. I'm sorry, this was beta over 2. This would be beta VGS minus VT minus VDS over 2 times VDS. So, but sort of like a very nonlinear resistor. So basically, your change in voltage with respect to time looks like you've got an RC circuit, which has got this sort of exponential time response, which is what you see here. And so you get this current that's flowing, and as the drain source voltage goes down, so as the supply as you're pulling this capacitor up, the drain source voltage for this gets smaller and smaller. So this is getting closer to VDD. This drain source voltage is getting smaller and smaller, so the current through the device goes down. And sort of when you get to this point, the transistor is on, but both sides of the transistor are at the same value. They're both at VDD, so you're not going to get any current flowing through the resistor. Okay, so this is what the current profile of the PMOS looks like. As this guy is turning on, so during this process, the VGS on the device is changing. So it's going from like here to here to here. So the current, this saturation current is going up, up, up. When it gets to here, to its final value, it stays constant. It stays constant here for a while as it's in its final value. And then at some point, it goes into this linear domain. It gets small enough that you're in this area. And then the capacitor value goes up and up. And as the capacitor gets charged up closer and closer to VDD, the current drops. So the current's dropping. And then finally, both sides of this transistor are at the same value VDD. Okay, so that's this sort of operation here. Any questions about that? I think that's like, I always have a hard time describing. It's a pretty complicated scenario, but it kind of shows you guys as the device is transitioning with a finite fall time, how it's running. Okay, so it's going from a low gate source voltage in saturation to a high gate source voltage in saturation. It stays at that highest gate source voltage in saturation. As long as it stays in saturation, then it goes into linear domain. And the linear domain, because all along you are, this thing as it goes from 0 to VDD, all along you're shrinking VDS of this device. Okay, so it's always, you're going like this down these curves. So you start with this curve, go to that curve. It's kind of like this if I draw it. Let me just, this is like a, what do you call it, piecewise linear approximation, but what it's kind of doing, the current is like doing this. Okay. Sort of a dynamic situation. Any questions about that? That's like sort of a complicated transfer function or response. No? Okay. So as I go through this in detail, because I think it's hard to get your head around all these operating points that this thing has, but this shows it pretty well. Okay. Now, when the next step is we're still on this PMOS curve with respect to time, what happens is the NMOS starts turning on. So we're not showing the current of the NMOS. This is this next graph here. But at some point, and the PMOS is turning off, let's say we're here. Remember that at the midpoint, if we looked at our, so if you looked at our V in versus V out, kind of look like that for an inverter. And at this midpoint here, so this was both NMOS and PMOS transistors were on and in saturation. Okay, so that's, you actually have both of these guys are on and in saturation. That means you get the current that, you're charging still the capacitor, but you're also, some of that current's getting wasted. It's going straight from, this is like Kirchhoff's current laws. There's a, the total current in this node is this current that goes in here, but then there's also a current that's going down here. So this is this so-called short circuit current when both the NMOS and the PMOS are on. Okay, so the PMOS has this little bump of a current here when sort of you're meeting, you're at this point here. Okay, and that's your whole 1 nanosecond cycle for just the PMOS. Now, if you look at the NMOS, same thing kind of happens. There's a small short circuit current when both the NMOS and the PMOS are on over here. And then the curve is the same as the PMOS. First you start in saturation, and then you go into linear, and then you discharge. In linear, and goes down to 0 as the drain source for this guy. As this V out goes close to ground, the drain source for this guy drops, and so the current goes to 0. Okay, so that's the current through the PMOS. That's the current through the NMOS. So if you look at the total current, okay, it's kind of the sum of these. This is the capacitor curve. Okay, so first there's no current, then the PMOS turns on. This current charges up that capacitor. Okay, so this is the total current going to the capacitor while the PMOS is doing it. The NMOS is off during this whole cycle, so it's not doing anything. And then when the NMOS turns on, this whole current leaves the capacitor. So you get this current. This current is leaving the capacitor. So I get this thing. So this is PMOS current, NMOS current, and the current on the capacitor. These are all transient currents, okay? So when we go from current to power, what we're doing is we're just multiplying the current by the power supply, okay? So this current, we're multiplying by, if we're looking at just the PMOS current, I'm sorry, if we're looking at the PMOS current, we don't multiply it by the power supply, but we multiply that instantaneous current by the instantaneous voltage again across the PMOS. So again, as this voltage goes from 0 to VDD, both the current's changing and the voltage across this device is changing. So it's just to get this combination. So it's basically your to have the I sub P, which is here, multiplied by the supply minus V out, which is the drain source of this guy, to show the power across the PMOS. Same thing with the power across the NMOS. Okay. And then this is the power sort of going in and out of the capacitor. And then this is the power from the supply voltage. And if you look at the power across the supply voltages, now that's the current of the PMOS times the supply voltage. Okay, so it looks, this curve looks a lot like just the curve of the PMOS current. This is getting multiplied by VDD, which is 1 volt. Okay, now the supply, VDD, doesn't see the current going through the NMOS at any point, or the power going through the NMOS, because it's at those points, the supply is this, as when the NMOS is on, pulling power or pulling current, the PMOS is off, means the VDD, the supply, doesn't see the NMOS. So the supply voltage doesn't see this. Okay, it just sees the current going through the NMOS. Okay, and then finally, if we actually calculate the total energy to charge and discharge the capacitor, you have to look at both of these guys. And this is the energy coming from the supply. Okay. And I think the critical thing to see is the energy stays flat after the PMOS has done its job. And the only power that comes out of the supply is during the PMOS being on cycle. So those are sort of like the two important things out of this, all this detail. Okay. So let's see. Look at my notes, make sure I'm talking about everything I want to talk about. Oh, yes. Talk about that. Okay, so when we're looking at this, when we're looking at sort of one step above, let's say we have this input of a certain frequency, okay, and we want to look at for that input, how much power consumption does this thing take? So basically what we do is we basically look at the power, the instantaneous power, we integrate it over the period. So this T is equal to 1 over F, the switching frequency. Okay, so this would be If this is the frequency, this is the period. T. Okay, so over that entire period, we want to look at what is the power consumption. Okay, and this is the power consumption coming out of the supply. So this is what your battery has to supply, or your power supply has to apply. Okay, so we go over this period, and we're like calculating what is the power anyway. VDD is constant, so it pops out, and we get the instantaneous current. Okay, and since we know the power over, across our full switching, so we basically know that the energy from the supply is this. Okay, so we basically end up with this. We end up with the CV squared F value. So this is the critical equation. So this was like sort of seared into every chip designer's brain, CV squared F. The V being the power supply, F being your switching frequency, okay, and capacity, C being your load capacitors. Okay, so this ends up being the power consumption of a CMOS circuit operating at a certain frequency with a certain capacitive load operating at a certain supply voltage. Okay, so notice it doesn't have a few things which always surprised me, but it's pretty. I guess it shouldn't be too surprising given what we're looking at, how we drive this. One of them is that there's no dependency on the size of any of our devices here, right? We could have made this. Well, it contributes to the capacitance, but besides that, we could have made these really wide. It doesn't. There's no resistance or device size. There's no information here about these two devices, right? It's only about the capacitance you're driving and the frequency at which you're driving and the power supply. So this is always, I always found this very interesting, that, basically this resistance or whatever you got here, it's not part of this equation at all. So again, it doesn't matter the size of these devices or anything. It just depends on how fast you're charging and discharging this capacitor and to what value you're charging and discharging it to. And I guess one way to think about it is, if these are really big devices, so you're pulling a lot of current, then you charge this very quickly, and you're only taking out power while you're charging it, and then the power consumption stops as soon as you charge it to VDD. So, or if you have a small amount of current, it'll take you longer to charge up, but you've got this current, either a small current that takes you a while to charge up the capacitor, or a lot of current that's very quick to charge up the capacitor, is the way I look at it. But again, this is like the main equation for power consumption in CMOS logic circuit, CV squared F, okay, for each capacitive load. So now let's say, I had a billion of these devices on my circuit. It doesn't matter how big those devices are. All I really need to know is those billion devices are driving a billion capacitive loads. So all I have to know is what's the total value of all those capacitive loads they're driving. Not that easy to figure out, but that's all you need to know. And how fast my the circuits are operating on average, and the power supply. And then you can come up with an estimate for the power consumption. Okay, so this is the most important equation. That's what it looks like. Okay, no dependency on transistor size. Okay, so now we need to kind of refine this thing. We're going to use this to, let's say, estimate our power consumption in our chip. And again, once you have, like, you've designed your chip, it's already in the database, you're building transistors, they're all, just doing what you wanted to do. It's in your computer-aided design tools. There are automated tools to calculate, try to estimate the power consumption. But like the rest of all our estimation tools, this is for before you start your design. What you want to know is like, hey, at this clock rate and this complexity of a chip, you're trying to estimate what your power consumption is going to be. Is this going to be over my power budget if I go down this path? Because once you've designed your circuit, it's too late. 6 months down the line, you've already spent your millions of dollars, and that's the wrong time to figure out if you're going to meet your power budget. So you need some further refinements of this things, because not every circuit is running at the full clock rate, right? Let's say you've got a circuit, let's say your chip is running at a gigahertz for the sake of discussion. If you multiply every capacitor by your supply square times a gigahertz, you're going to get a really big number. But you got to remember that the majority of the circuits are just sort of sitting there quiet. They're not switching. Now remember that the only time we're taking up power in this cycle is when the PMOS is driving this load from 0 to 1. If the circuit is just sitting here, there's no power consumption. There's no transient power consumption, okay? So they've come up with this concept of activity factor, okay? So that's sort of compared to a clock. Let's say the clock is F. There's this activity factor where it says how active is that circuit. So for example, let's say if our baseline is a clock. So for a clock, the activity factor by definition is 1, okay? Now, let's say you had purely random data, or let's say not purely random data, sorry. If you had data transitioning in every cycle of the clock. So because our flip-flops are only running on edges, you would only, the fastest the data could transition, so this is the fastest data transitioning, is at half the clock period. So even your fastest data would only be running at an activity factor of 1/2. Okay, and in fact, because I guess you could say that you have like random data essentially in a full circuit, what people typically use is an activity factor of 0.1 for the chip, or sort of a number that's 10% of this value. Or if you know, as we'll see in examples, or if you specifically know that a circuit runs this percentage of the time, you can actually take it as the activity factor. By the way, a couple of important things here, and I should point out. So back to the circuit for a second. So back to this equation for a second. Notice that the power consumption is linearly dependent on the capacitance and the operating frequency, but it's square law dependent on the supply. So if you somehow manage to get absolutely the same circuit in a 180 nanometer process, for the sake of discussion, say same C and same switching frequency. So 180 nanometer process, supply is 1.8 volts. So VDD squared is 1.8 volts squared. I always forget what this is. Is it 3.6 volts squared, something like that? I think it's something like that. And let's say you compare that to a 65 nanometer process, which has got a VDD of 1 volt. Here, VDD squared is 1 volt squared. So just because of your difference in supplies, the power consumption of this guy is a factor of almost 4 higher than this guy. So huge difference in power consumption, depending on process, i.e. supply voltage. So again, just because the supply is higher for a older process, the power consumption just from that is significantly higher, okay? Because it's got the square law dependence, like a factor of 4, it's huge, okay? Now, furthermore, even if you were able to run this guy at the same frequency as a 65 nanometer process, maybe you can, just because all your devices are bigger, your capacitances are also going to be probably higher in this 180 nanometer process. So they're probably also going to be driving higher capacitor values in total across your whole chip. But the biggest difference in power consumption, and it's a huge one, is the supply voltage. So the supply voltage is only going, it's not changing that much, but because of the square law, your power changes quite a bit. So that's like a very, very important thing. And also we know that as your the older processors are lower cost, so that's a good reason to go try to use those. But then you see that sort of trade-off between cost and power consumption. So that's one possible area to see. Okay. Okay, just I think somebody a while back also mentioned this. I forgot who it was. That when both, when we're looking at this transfer curve for the inverter, at some point both the N and the PMOS are on, so they're both on, and you get this short circuit current when both N and P are on. And in fact, we kind of see these little blips here, which is a short circuit current while they're both on. You get this kind of transient current that goes from the supply to the ground. But what we're saying is and as this thing shows, is it actually turns out to be not a very large number. So we typically end up, a lot of times I thought it was the short circuit current that would be driving the power consumption, but it's really not a huge amount of the power consumption. The huge amount of the power consumption just comes from the charging and discharging of the capacitor. Okay, so that's the sort of switching power consumption. As like, again, let's say you have your chip. It's got, I don't know, 1 billion gates, say. Let's say in a typical operating characteristic, you've got, only 10% of the chip is operating and running fast at your full clock rate. Chip running is pretty typical. And, 90%, no, not transitioning. So this is nice because this means that if I just use these numbers, it means that when I do my my switching power, I can use an activity factor of 0.1, right? Just based on these numbers, only 10% of the devices are running. So, if I have the total capacitance on the chip or C, the chip is running at some frequency, at some supply, I can just say my switching power consumption is only a tenth of this, which is cool. Okay, so that's my switching power consumption. But that's not my whole power consumption. If you remember from the transistor, these we had a whole lecture or maybe several lectures on the transistor characteristics. So there's a certain power consumption that the transistors have when they are operating. But then if you remember, we also had a significant leakage current. So this 90% of devices that are not transitioning, they don't have any switching power component, but they do burn power still from the leakage currents. Okay, so those two different powers are called the dynamic and static power. The reason it's called dynamic power is, the switching, we only get power consumption from the active circuits when they're switching. So there's a dynamic event happening. But there's also power consumption because of this leakage, even when there are certain circuits that are not running and they're sort of in a static operating mode. Okay. Now the dynamic power we just talked about, it comes from the switching power. So that's the alpha CV squared F. Okay. And this one we said is like, 10% of switching power. And we said sort of, you still have to keep track of it, I guess, but we just said it's negligible for the most part. Okay, so that's all these components. Now, these components, what are these guys? Well, we've got all the leakage powers times the supply. And again, going back to our earlier lectures, we have subthreshold leakage, we have gate leakage, we have junction leakage. So basically all the leakages times the supply. Okay. Now, for each individual circuit, again, all these currents are much lower than the current of our active devices, but there's a lot more devices that are in this state than they are in this state. So this ends up being, especially at the tighter processes. So I said, look, if you're going to, we talked about, if you're looking at this dynamic power consumption or switching power consumption, it's a lot lower in the 65 nanometer process because we're at a lower supply voltage. But it turns out in these tighter processes, the leakage current is higher. Again, we talked about that in our transistor lectures. So So basically that's sort of a trade-off. Then you go to tighter processes, your smaller processes, their leakage current goes up, so your static power goes up, but your dynamic power drops. So each one is there's a trade-off. Okay, so guys, let's try to do this. I think I have let's do a couple examples. So why don't you guys try doing this for a couple of minutes, and then maybe I'll ask one of you guys to try to help me out here. So let's say this is the example. And if you want to cheat, I think the answer is in the next slide. But anyway, so we have a 1 billion transistor chip. A small minority, so 50 million of the transistors are logic functions, and the majority of chip is memory transistors. That's dynamic memory, like, sort of the memory in your computer or whatever, you got 64 gigabit of memory, so that's the memory. So 950 million transistors are memory, only 50 million are logic, okay? They are, the average size of the transistors in your logic circuits are 12 lambda, and you can pick, let's see what's we need to pick. Let's pick, it's a 65 nanometer process, so say lambda is, what is it? Let's call it 30, let's call it 40 nanometer, I think, is a lambda, based on lambda base rules. Okay, the activity factor of the logic is fairly high. The memory is only accessed every once. So the memory, look at the memory transistors are smaller on the average than the logic transistors. And they're also activated less, okay? And then, so this is the capacitance per gate and diffusion. And we want to basically, what the goal is, we want to estimate the dynamic power consumption, okay? So let's say, how do we do this? Okay, remember the dynamic power is almost entirely the switching power. So that switching power is the activity factor. So this guy, times the supply voltage squared, times the capacitance, times the operating frequency. So the FSW is given, right? That's given. Supply is given. Alpha is given for each type. Now for each circuit, now we got to figure out the biggest part of this is the C, okay? So for each circuit, you have an average size. So 4 lambda is 4 times 40 nanometers, okay? And then this has a certain capacitance associated with it. So from there, we can get the capacitance of a memory transistor. And then we'd have to multiply it by the number of memory transistors to get the capacitance of memory. And then to get the capacitance, the total capacitance of logic, we do the same thing, except it's 12 lambda times 40 nanometers times total number of logic transistors. Okay, so why don't you guys give a shot at that? Take a couple of minutes trying to calculate what the dynamic power is, and we'll try to solve it. Wait, let's see, 25. Okay, sorry guys. This instead of lambda of 40 is a lambda of 25. Sorry. Okay, guys. Let's try to do this. Why don't I pick on a hyzer? Are you game? Hyzer, are you there?
Hello. Oh, sorry.
Oh.
I had to look for my calculator. I am not done with my calculation.
No worries. So let's calculate this thing. So what did you do? So we have, I think the thing to do is to figure out these capacitances, right? C total for logic and C total for memory. So do you want to give it take a crack at it? How do I? Okay. So C logic total. What's
For
what?
C log.
Go ahead. Sorry.
Yeah. I was gonna say for C logic total, it's 12 times 40 nanometer times 50 million, right?
12 times. Yeah. So I set you guys wrong to begin with. We should use 25 nanometers for lambda.
Oh yeah. Sorry.
Right. So times 25 nanometers per lambda times 1 femtofarad per micron plus 0.8 femtofarads per micron. So this is these two guys. So this ends up, this is the, so this is the capacitance for one logic transistor. And then we multiply that by 50 million, like you said. Which I guess that ends up being 27 nanofarads. Okay. So how about the memory? Heiser, you want to take a shot at that? No.
Yeah, sure. Would that be 4 times 25 nanometers? And then I'm assuming plus or times 1 femtofarad plus 0.8 femtofarads.
So I'll write it at 1.8 femtofarads per micron.
Yeah. And then times 950 million.
And that ends up being 171 nanofarads. And you can already see like there's the transistors in the memory are smaller, but the total capacitance in the memory node is what, like a factor of, I don't know, 5 to 6 times higher, right? More capacitance in the memory. Okay. So then what does a dynamic power then look like? For each. Let's look at the logic first.
Okay. So, well, starting off with VDD.
Yep.
Wait, what was VDD again?
It's 1 volt.
Oh yeah, right. Yeah.
So we have.
So once.
Don't forget.
Yeah, 1 square
Mhm.
times 25 nanofarads.
Yeah, 27 nanofarads. Okay.
Oh my bad, 27.
And then
Times the switching frequency.
yeah, it's
which
gigahertz.
1 gigahertz, and the
So
alpha
is 10 to the
point
9 hertz.
point
Yep, times
0.1.
0.1. Oh, sorry, an activity factor. Yeah, it's 0.1. Correct. Okay. And then this is added to the memory, which
All
is
right. So 0.02, the activity factor.
Yep.
Oh yeah. Okay.
0.02.
0.02.
Okay.
For the capacitance, it'd be 171 nanofarads. And the switching frequency, once again, 1 gigahertz.
And all this ends up being 6.11 power consumption. Okay. Thanks, Heiser.
Yeah, no problem.
So notice how much of a break we got from a couple of things. From just this activity, like this memory was this huge capacitance. Okay, because there's a lot of them. Okay, but if they were running all the time, if this activity factor would have been a half or a 1 or something like that, this thing would have just blown up. And in fact, you see that when you're doing your designs, that like memories really can suck up a lot of power. So you got to be careful how fast you access your memories, how often you access your memories. Fortunately, you can only access your memory sort of 1 bank at a time, and typically 1 word at a time. Okay. And then the logic, although there's a lot less logic, they're running sort of more often, but still, the majority of the transistors are off. So this, if you guys, get a chance, you might want to run this without the activity, with the activity factor of 1, and you'll see this thing ballooning to, I don't know, it'll be like hundreds of watts of power consumption. So I think that's the kind of things you see, is that the fact that your activity factor is low in most of your devices really helps you out. Okay, guys, so I think I'm going to stop here. We're getting the next one. We're looking at sort of the different ways we can reduce the activity factor and the sort of static power. So that will be on Thursday. So any questions, guys? No? Okay, if not, I'll let you guys go. Good night. Bye, guys.